Chapter 9 Climate Regions and Climate Change. Section 9.4 Causes of Climate Change. So in this video lecture, I'm going to try to explain to you how there are a variety of different factors that can cause the climate of our planet to change. These mechanisms work in different ways. Some of them are connected to each other, some of them are separate. I'm going to present a model of these mechanisms and suggest that we can categorize them either as being extraterrestrial factors or factors that operate within the Earth's ocean, atmosphere, and land surface. So let's begin by just briefly talking about some of these extraterrestrial factors. The most obvious factor that could change the Earth's climate is changes in the sun's output of solar radiation. Now, we've well documented that there are some minor changes in output over short periods of time, and we have some proxy data to suggest that maybe over longer periods of time, the sun's output may have caused cooling on our planet, the cooling that occurred during the Little Ice Age. It's possible that solar output was 1% lower than it is today, and that would account for those cooler temperatures. Serbian mathematician Milan Milankovic in the early 20th century examined how various geometric relationships that exist between the Earth and the Sun may cause climate change. And this climate change is driven by changes in the amount of radiation received at different parts of our planet. He found that there was 3 cyclical events, and if you put them together, they may have been they may have caused enough change in solar radiation that they were responsible for the ice ages and the periods of warming in between these glacial advances that occurred in the last 2.6 million years. There is a theory out there that maybe the Earth encounters increases and decreases in interstellar dust that exists in the voids of space between the Sun and the Earth. When it's more dusty, it causes a reduction in solar radiation. If it's less dusty, an increase in solar radiation, which would lead to a warmer climate. Scientists have theorized a number of internal factors that may be important to changing the Earth's climate. Volcanic emissions. Volcanoes can release two gases, sulfur dioxide, which has now been found to cool the climate for short periods of time. Or maybe volcanoes have released in the past, and there's evidence to suggest this, carbon dioxide. And maybe volcanoes in the past were responsible for short or relatively short periods of warming on a geologic time scale. We know that mountain building has occurred at various times on our planet. There was a period when there was no mountains on the west coast of North America. If we had no mountains, that would completely change the climate that we see on the leeward side of the mountains. Calgary, Edmonton would be much warmer and have more precipitation if there was no mountains. Continents on our planet move about because of continental drift. Antarctica in the past was at a different location. It hasn't always been centered at the South Pole. And that would, of course, change the climate of that continent as it moves around. We know the atmosphere and ocean are involved in dynamic exchange of heat energy over short periods of time and long periods of time. El Nino La Nina cycles are an example of this, examples of heat exchange changing, and they occur over short periods of time. There's something called the Pacific Decadal Oscillation, which occurs over decades, changing the way that heat moves between the ocean and the atmosphere. Humans have caused changes in atmospheric chemistry. We've increased the amount of carbon dioxide, methane, and nitrous oxide in the atmosphere, which has enhanced the greenhouse effect. But the greenhouse effect also changes due to natural variations in carbon dioxide that are driven by the temperature of the Earth. And I'll talk more about those shortly. The atmosphere may change over time in terms of its reflectivity. Maybe there were times when there was a lot more cloud cover, and that reduced the amount of incoming shortwave radiation. We know that the surface of the Earth has changed in terms of its reflectivity. The snowball Earth theory is related to a cooling of the Earth that causes a positive feedback mechanism where more snow is produced, increased albedo of the Earth's surface, leading to even cooler temperatures to a point where the Earth almost freezes over right to the equator. Anyways, well, we're going to focus in on 4 mechanisms of climate change, and these are mechanisms that are important in explaining climate change that has occurred since the beginning of the Pleistocene. And these mechanisms include the variations in Earth's orbital characteristics that were studied by Milan Milankovitch, changes in atmospheric carbon dioxide, both natural and human caused. We'll look at short-term variations in climate that can occur because of volcanic eruptions that release sulfur dioxide in the atmosphere. And then finally, we're going to look at variations in solar output. And variations in solar output may explain the cooling of the climate that occurred during the Little Ice Age. So let's begin with variations in Earth's orbital characteristics. As I said, this was studied by Milan Milankovitch, a Serbian mathematician, in the beginning of the 20th century. And his theory suggests that normal cyclical variations in 3 of the Earth's orbital characteristics with the Sun are probably responsible for some past climate change. In fact, responsible for the glacial advances and glacial retreats that have occurred during the Pleistocene. The basic idea behind this theory assumes that over time these 3 cyclical events work together to change the amount of solar radiation received on the Earth's surface at different latitudes, and mainly it's the middle to high latitudes. So what are some of these cyclical variations? The first one is called eccentricity, and this relates to the shape of the Earth's orbit around the Sun. This shape can vary over a period of 100,000 years, and the orbit of the Earth around the Sun can vary from being nearly circular to elliptical. The greater the eccentricity of the orbit, the greater the variation in solar radiation received between the time when the Earth is the closest, perihelion, or when the Earth is farthest, aphelion. So we would expect a more constant climate with a nearly circular orbit. In a highly elliptical orbit, if this occurs at the right time, it could cause a cooling in the northern hemisphere, which causes the buildup of snow and ice at high latitudes, leading to glacial advance. The second cyclical variation results from the fact that the Earth rotates on its polar axis, and this axis moves around due to a wobble that's involved in the spinning of the Earth. This wobble changes the timing of equinoxes and solstices. This effect is also known as precession of the equinox. The precession of the equinox has a cycle of approximately 26,000 years. So this precession of the equinox changes the timing of when solstices, equinoxes, aphelion and perihelion occur over time. And in the top graph, we can see the timing of these events 10,000 years ago compared to C, which is today. The third cyclic variation is related to changes in the tilt. The Earth's tilt can change between 22.2 and 24.5 degrees relative to the Sun and the plane of the ecliptic. Right now, it's in the middle at about 23.5. When the tilt is smaller, there is less climatic variation between summer and winter seasons in the middle and high latitudes. This condition is believed to cause increased growth in alpine and continental glaciers, that a mild climate is required for snow to build up, and if summers are cooler, less of that snow melts, causing the buildup of these glaciers. If the tilt is more extreme, 24.5 means warmer summers, more heat energy available to melt the snow and ice that accumulates during the colder winters. Let's now look at variations in atmospheric CO2, the second factor. In the 1970s, there was a project involving many scientists where they analyzed deep ocean sediment cores and proxy data in these cores to determine past variations in Earth's global temperature. And these cores went back about 400,000 years. And the following pattern was revealed in these cores. That relative global temperature varied over time. There were short periods when temperatures were warmer, these periods of glacial retreat, and then periods when the planet was much cooler and glaciers advanced. So for example, if we look at the bottom graph, we can see the most recent period, the Holocene, and then prior to that, at about 120,000 years before present, there was another warm period. In this core, they also discovered that there were variations in how much CO2 was found in the atmosphere. And you can imagine if there's more CO2 in the atmosphere, it's going to lead to a warmer climate. If there's less CO2 in the atmosphere, it's going to lead to a colder climate. So there seems to be variations in carbon dioxide correlated to glacial advances. During glacial advances, carbon dioxide in the atmosphere went down. And then for some reason, during glacial retreat, when things warmed up, carbon dioxide went up in the atmosphere. So this acted as a positive and negative feedback mechanism. So what was happening? What they discovered was that the Earth's temperature was changing because of the Milankovitch cycles and variations in solar radiation. And when the temperatures became cooler, carbon dioxide moved from the atmosphere into the ocean. Ocean waters actually can dissolve or take up more carbon dioxide when they're cooler. When ocean waters warm up, they release carbon dioxide into the atmosphere. So they found that there was about a 30% variation in how much carbon dioxide there was in the atmosphere, depending upon whether you were in a warm period or a colder glacial period. And the oceans were the major store of carbon dioxide on the Earth. So the amount of carbon dioxide held in the oceans is a function of temperature. Carbon dioxide is released when global temperatures become warming, and this acts as a positive feedback mechanism. CO2 diffuses into the ocean when temperatures are cooler. And this leads to a negative feedback, causing the temperature drop triggered by the Milankovitch cycles to even result in a greater temperature drop because there's less CO2 in the atmosphere. Now, we've also been modifying, humans have been modifying the amount of CO2 in the atmosphere, and that's most recent. That's in the last 300 years, due to our emissions from fossil fuels and changing the amount of natural vegetation on the planet. We have been enhancing the greenhouse effect. And here we can see a record that we have from measurements made on top of Mauna Loa volcano in Hawaii. And that trend line is related to the amount of carbon dioxide that we've released in the atmosphere from two processes, as I said, burning fossil fuels and changing the amount of natural vegetation on our planet. We're replacing it with cropland that stores less carbon dioxide. The third mechanism I want to talk about are volcanic eruptions. And we're going to talk about volcanic eruptions that have occurred in the last couple hundred years. And early on, even in the 19th century, scientists noticed that after a large volcanic eruption, especially if it occurred near the equator, that you would get cold years following the eruption on the planet, cold summers. For example, the Mount Tambora eruption in 1815 caused cold weather to occur in 1816 and 1817, and 1816 was actually known in the U.S. as the year without a summer. The summer was short, it was poor, temperatures were cold, crops didn't do well that year. So what's the connection? What's the connection between volcanic eruptions and short-term climate change? Now, these eruptions need to be explosive. They need to be large eruptions. And as I said, it's important that they occur around the equator. Now, originally, climatologists thought, well, it's the dust. It's the dust that's emitted. It's responsible for reducing the amount of shortwave radiation coming into the atmosphere and being absorbed to the Earth's surface. Well, they found out that the dust actually washes out of the atmosphere in a short period of time, few months. So this climate change was occurring for years, a couple of years, 2 to 3 years after eruption. So it's got to be something else. And what they discovered was that some eruptions also release sulfur dioxide gas. Now, sulfur dioxide is a gas. When it goes in the atmosphere, it can remain in the atmosphere for up to 3 years, and it needs to enter the stratosphere. So that's what the data indicated, that if the sulfur dioxide gas is released by a volcano, goes into the stratosphere, it can cool the Earth's climate. So atmospheric chemists figured out what was happening was the sulfur dioxide was mixing with water vapor to form sulfuric acid, and then that sulfuric acid formed a layer around normally occurring very small dust particles that were in the stratosphere. And this made them optically bigger. And they started reducing small amount of reduction of the amount of shortwave radiation penetrating through the stratosphere. They created, these particles formed a haze layer, and it reduced the transmission of shortwave radiation from the sun. So one cloud that was, volcanic cloud that was monitored via satellites was Mount Pinatubo in the 1990s. And it was shown that there was a haze layer produced by it. Here we see a satellite image of that haze layer. So this is optical depth, where pink and red being less optical depth. The atmosphere is not clear in these areas. And this reduction in shortwave radiation cooled the planet for a short period of time by about 1 degree Celsius, maybe 2. The eruptions need to occur at the equator because if they occur at the equator, the air currents in the stratosphere move air from the equator to the pole, so they distribute it over a larger portion of the Earth. If the eruption occurs at too high of a latitude, then it only influences a smaller portion of the planet, in whatever latitude, let's say 60 degrees and above. We can find a record of past volcanic eruptions because this sulfuric acid deposits itself at the poles. So air moves in the upper atmosphere, in the stratosphere, from the equator to the poles, and then at the poles the air descends, and it leaves behind this trail of sulfuric acid that was once a haze layer in the atmosphere. So some previous eruptions include A, Krakatoa, B, Santa Maria, C, in 1963, Agung, 1981, El Chinchon, and then 1993, Mount Pinatubo. The final factor I want to talk about in terms of climate change is the sun. And this one seems obvious, right? If the sun's output varies over time, it's going to influence the climate of the Earth because solar radiation is the main source of energy that heats the atmosphere. So we've been measuring solar output since the 1980s, 1990s using satellites. And what we've found is the sun does indeed vary in terms of its output. However, the amount of variation that we discovered since the 1980s was not enough to cause drastic changes in the Earth's climate. The decrease or the variation in solar output was in the ballpark of about 0.1%. And this cycle seems to be about 11 years in length. So here we can see variations in the amount of radiation since about mid-1970s, based on several different measurements from different satellites. And we can see that the amount of solar radiation variation is about 2 watts. So that might be enough to cause a 0.1, 0.2 change in global temperature. Not enough to really be considered significant. However, if we could increase this variation in solar output 10 times so that it's 1%, that could cool the Earth's climate by 0.5 to 1 degree Celsius. And scientists believe that there might have been a 1% variation in solar output back in the Little Ice Age, between 1650 and 1750. And the evidence they have is sunspot activities. So sunspots vary, and their long-term average, the more sunspots there are over a period of time, the more output from the sun. So those sunspots don't block radiation. The more sunspots indicate a more active sun emitting more radiation. When there's a lack of sunspots, that's when radiation output decreases. And during the Little Ice Age, there was very little sunspot activity. So scientists were taking note of the number of sunspots, and there was a minimum called, and it was named the Motter minimum, a lack of sunspots between 1650 and 1750.